ions, so that is an increase in entropy, right, because you have more particles. But then you have the water molecules around it that has a huge decrease in entropy. So the entropy of the universe, when you have the system plus its surroundings, ends up being a little bit negative. When you take the universe to be the space around your reaction. Okay? And so we kind of have to take into account what's happening to the system and surroundings sometimes. So for ions that have big charges, +2, +3, we tend to see a net decrease in entropy when you do it predicted. We have to tell you that, otherwise you make the wrong predictions. Okay. Number 9, you guys in the back. What is this reaction?
Wait, so what was it?
Well, yeah, for our case, it's positive because the charges are +1 and -1. So then, yeah, that would have to be +3 and +3 definitely.
So if you were to have like magnesium chloride, would that be a negative?
That's right.
Okay.
When it dissolves, it'll probably have a negative entropy change. Okay, so that has to be. But then ours happens spontaneously. You guys in that?
What? For what question?
The ammonium nitrate. It dissolves
For number
spontaneously?
9? Yes.
Yes. Okay, because you just mix it and it's gone, right? Number 10. Was heat transferred, you guys up front? How was heat transferred? System to surroundings or surroundings to system? Surroundings to system. Okay, and what do we call that? Endothermic. Okay, good. And then the delta H for endothermic reactions is positive. Okay, so delta H is positive when the heat flows into your system, and when you hold something when you have an endothermic reaction in a flask and you hold it in your hand, you will feel cold because heat's going from your hand away into the test tube. Okay, that's what cold feels like, it's away from you. If it was exothermic, heat will flow into you, and that's going to feel hot, right? Because heat flowing into your hand. And then enthalpy diagram, right? We got the solid crystals. We got the ions, and we got the crystals going to ions. Products are higher energy than the reactant, right? Because it's endothermic. Energy is being added into the system so that you can actually work it out. All right, and so the guts of this is the last few questions here, 13 to 16. Okay, that's where we really want to focus on because we want to get you thinking in this way. So, what does 13 say? Does the enthalpy for this reaction contribute to being spontaneous? You guys are back. No, did I call you guys right? No, right? You guys now. Okay. Does the enthalpy term help you to be more spontaneous in this reaction? You guys ready? What do you guys reckon?
The enthalpy term does not contribute to the reaction being spontaneous except positive value.
That's right. Okay. So the answer is no. Now we'll see why in a few more questions later. We'll kind of really put it into perspective. Okay. So what is driving this reaction? You guys up here.
Entropy.
The entropy must be driving because we know that this happened by itself. Okay. And so delta S must be what sign of this reaction? You get positive. Positive. Right? Now, I know one of the big questions that came up is what do we mean by favorable and what do we mean by what drives this reaction towards spontaneity? So spontaneous reactions have negative delta G's. Okay? Doesn't matter where this term comes from. You'll see where it comes from in the video tonight and tomorrow when you watch. But what's important is how do these terms get you to a negative delta G? If they lead you towards a negative delta G, that means those terms are favorable for spontaneity. So what two signs here would have to be favorable? For delta H, would it be positive or negative? How would it be favorable to, in order to be spontaneous? Anybody? Why would you say negative? Anyway.
I don't know the mathematical law, but
If you're at zero Kelvin, right, that right-hand term goes away. But if you're exothermic, what is delta G at that point? Positive or negative? It is negative. So we still would say it's spontaneous, right? Even though reaction won't happen at 0 K, as we get closer and closer to that, delta G is still negative, so the reaction is still spontaneous. Now, if I flip it on the other way, right? Knowing that this is negative, what sign should delta S be so that this difference will always be negative? If delta S is positive, we know temperature is always positive, so that whole term is positive. So a negative number minus a positive number will always be negative. Which means it's always going to be spontaneous, no matter what. You see how that works? Just look at the signs. Okay, like I said, you get actual numbers coming pretty soon. But if you understand how we do the analysis with signs, it'll give you a really good gut feeling for what happened now and interpret that. Okay? So, for our reaction, delta H is positive, delta S is, you say it was positive, right? Now, let's see how we interpret this. So we said delta S is positive, delta H is positive. We know that this reaction was spontaneous because it happened, we saw it happen, which means that delta G has to be negative. Okay, that's just by definition. So what will we say that delta H is in our case here? Is it favorable or unfavorable towards spontaneity? Delta H that's positive, it's kind of acting against being spontaneous, right? It's raising the delta G, increasing it, so we say it's unfavorable. But the positive delta S, what do we call that? We say that's definitely favorable towards spontaneity. In fact, that term is actually, we would say probably, so that the positive delta H matters, so we get a negative. Yeah.
So is it whichever one is favorable is the one that that contributes to the reaction being spontaneous?
Yes, if it is spontaneous.
If
Right, so if you see a reaction actually happen, and you say, we saw this case in this scenario, we say, okay, well, it's not the delta H that's causing it to be spontaneous, because that's positive. But it's this big positive delta S that's causing this T delta S to be bigger than the delta H, so the difference is negative. That's what's causing the reaction to go. Okay, so when you have to wait, which factor is more important? In this case, it's the entropy term, when this guy dissolves into ions. That's actually driving this reaction. And then would this reaction would you end up on? What did you guys end up on? Did you guys answer last one? So you guys up front there. Number 16. What did you guys hear for that?
spontaneous at higher temperatures.
So they said spontaneous at higher temperatures. Let's make sure they're right. Okay? T can be small or it can be big, right? And small, I'll just say 0 is small. That makes it easier, I don't know. Right? So at low temperature, say make this thing 0, that right-hand term goes away, that's positive. So that means delta G is going to be positive. So not spontaneous anymore. Well, now T is really, really big. Say, I don't know, big, just, I don't know what the size of this guy is, let's say in the millions. Then this product will probably be really big, and that means this difference will probably be negative. And if it's not negative, you can probably hook up a bigger T such that you make the difference negative, right? So that means at higher temperatures, this reaction is spontaneous. At lower temperatures, you probably can find a cutoff if you actually have the data at which this thing is not. Okay, so good. It's going to be spontaneous at high temperatures. See how that worked? But that's how we got to look at this stuff. So let's repeat. A lot of these questions are the same. You probably noticed that. Right? So let's write the reaction up. So there's our reaction. Is that the molecular or ionic? There's the molecular. Okay, so what does the ionic one look like? It's going to be solid magnesium plus 2H plus, because the chlorides are spectator ions. Okay, that's going to look like that. There's a net ionic. Was this reaction spontaneous? It happened, right? Drop the magnesium, you see the bubbles, and it went by itself. You guys in the back. Number 19. Was it exo or endothermic?
Exo.
You got warm. So what's the sign of delta H, you guys again?
Negative.
So exothermic reactions are negative. And how we draw the enthalpy diagram, that means the products are lower in energy. Right? So that means the magnesium plus HCl are up top, and the products are lower in energy, like that. Okay. Now, here's the tricky one, right? So, you guys up front, what would the sign of delta S be? Why would you say negative? Well, but what state is the H2? It's gas. Do gases have higher entropy than aqueous phase species? Probably. Okay. And we start off with the solid and aqueous, and we end up with a gas and aqueous. What would you say? It would probably be a positive delta S because you use the gas. And when you look at tables of entropy, the gases have many times quite a bit lower entropy than the aqueous or solid. Huh? Well, the system includes the H2 gas. Okay, so when we think about our reaction, it includes both of these guys. None of it's escaping. Okay. So delta S, I would say, would be positive. Now, what is the driving force for this reaction? Okay, so we said it's exothermic. So the heat dispersal is driving this reaction. But what about particle dispersal, delta S? Is that also helping this reaction be spontaneous?
Yes.
Yes. Because what's the sign of delta S that I would expect to see? Positive. Is that favorable? Right, so both of those terms are actually helping this reaction be spontaneous. So in this case, it's both. Enthalpically favored, that's the delta H, and entropically favored from the delta S. Okay? So it's both. And then we want to summarize based on that equation. Okay, so delta G, because this was spontaneous, we know this was negative. Delta H, we know it's exothermic, so this was negative. And the delta S, we know it was positive. Right? Are there conditions? So, was it you guys up front, Egyptian? I think it's you guys up front, right? I called them last one, so.
No, it's them.
Okay, you guys get back. What's the answer to number 23?
These spontaneous temperatures,
Spontaneous at all temperatures. Why?
because regardless of the temperature, the right side of the equation will always be negative.
Because it's favored both, right? Delta H favored and delta S favored. So it'll always be spontaneous. right? Even when there's a 0, that's negative. And when it's really big, it's a negative minus a big positive, so which is still negative. Okay? Good. And then the last one. Notice, a lot less question, but same stuff, right? So, what's the reaction? This one's a funny one because a lot of you guys wanted to write a reaction. Like, try to figure out, okay, what is acetone reacting with? Well, what's going on? What is this process called? Evaporation. Evaporation is physical and chemical. It's a physical process. In a physical process, do you have a change in composition? No. So it's acetone in the beginning, it's still acetone at the end. What's the only thing changing? Liquid to gas. So it's acetone liquid was acetone gas. Okay? Once we got that cleared up, then we can move on, right? Was it spontaneous? Yes. Okay? You guys here. What did you see with the thermometer reading? Did it go up or did it go down?
Go down.
The thermometer reading went down, so it got cool, right? According to the thermometer. So what is the delta H for this reaction? Was it positive or negative?
Negative.
Huh?
Negative. Positive. Was it positive? I'm sorry. Let's look at that one.
So in terms of, you gotta think in terms of the thermometer.
Oh, yeah.
Because the thermometer is like your hand, right? So if the thermometer felt cold, so heat went from the thermometer to the acetone that was on the outside of it. Okay? So the delta H was positive because heat was going into the acetone from the thermometer. That's endothermic, right? So the enthalpy diagram here would have acetone gas. Acetone liquid. So there you go. Liquid to gas. Gas has a higher energy than liquid, right? It took energy to evaporate the acetone. Anybody, what is the delta S versus positive or negative? Positive. Gases always have higher entropy than the liquid because it's the same species, right? That should be a right? So now, delta H here was positive, delta S was positive. We know this thing was negative because it evaporated, right? Under what conditions will this reaction happen? Anybody?
Higher temperatures.
Okay? Now, at what temperature do you think this thing will stop being spontaneous? The what?
At 0 Kelvin?
Okay, well, a temperature higher than 0. Okay, what do we call it? There's a temperature higher than 0 than which this, for sure, I know won't be spontaneous anymore.
Room temperature.
What do we call that for acetone?
When delta H and T delta
Well, no, okay.
Specific heat.
Give me the name for that temperature.
Specific heat. I don't know.
Vaporization temperature?
The what?
Vaporization temperature?
Not the vaporization. The freezing point.
Freezing.
Once you hit the freezing point for acetone, instead of the acetone going from liquid to gas, guess what? It's going to go from liquid to solid, and this won't happen, right? You might get some sublimation, but that's solid to gas. That's a different process. Okay, and then there we go. We're done. Now, what do you need to do? Let's put this all together. So you understand this sign stuff. Okay, rationalize the sign of the delta G. I'll send out an email through sampling probably in the next 20 minutes. Once I got all the videos that I wanted recorded. I just have to update my webpage or just take a minute or so, the video to YouTube right after one by one. I'll send you an email, say which videos I want you to focus on. The rest of them, there's some examples in there. There's a couple of examples I didn't record yet that I won't right now. I'll probably report tomorrow maybe. And then there's some stuff that you already kind of talked about. But go ahead and watch it. It's stuff that makes sense. Watch them all. Okay, but I'll tell you which ones I expect you to watch based on where we are right now. And then on Wednesday, we'll spend one more day on chapter 12. we'll do a couple more computations, we'll do as a homework. The homework will be due at exam 1, because there's not that much time between now and the exam. So I'll make chapter 12 and 13 homework both to look at.
夏の空